All right, let's talk through some of the basics just of vectors. So let's just look how you symbolize a vector. This would be vector A. It has that little horizontal line and a little square on top. And you can give it in two forms. Vector A could be in component form, and it could be like 5, 12. And this is only a two-dimensional vector. 3D would just have another dimension, right? X, Y, Z. Let's just stay in two dimensions here right now. So this is the vector A, and it's 5, 12, right, on a graph. That would mean that the vector is 5 units long in the x direction and 12 units tall. So it might look something like that. And again, this 5 and 12 means that this distance is 5 and that distance is 12. Okay? You could also give it vectors in magnitude and direction form. Okay, so how do you mean the magnitude? So that's the magnitude of A. Now you might be used to thinking that is absolute value, but it's not. It's magnitude. It's the length of the vector. It's the size of the vector. And to find the size of the vector, hopefully you realize that this is just a triangle, and so we can do 5 squared plus 12 squared equals the length squared. And I did pick nice numbers. So the magnitude of A is 13. And then we could find the angle. The angles are always drawn with respect to the x-axis. So that's some angle theta. And theta in this particular case is something close to 67.4 degrees. And then you could figure out the radians if you needed to. Okay, so again, what is a vector? Well, a vector is different than a scalar. A scalar is just a number. A vector has both size, meaning magnitude, and it has direction. Almost everything we do in physics is a vector. Velocity, acceleration, force, momentum, angular momentum, torque, those are all vectors, meaning they have both magnitude and direction. It's not just enough to say that you're traveling 5 meters per second. It's 5 meters per second north, south, to the right, to the left, or at some random angle. Okay, so how would we actually break these things down? How do you go back and forth? Well, going from component form, and when I say component, I just mean I'm giving you the pieces, right? And again, these symbols indicate that it's a vector. If you use parentheses, it's more like a point in space. But this is the vector 5, 12, 5, 12. It has length 13, and it's got an angle with respect to the x-axis of 67.4. Okay, so first, let's just realize that if we do x squared plus y squared, we do in fact get the magnitude. Let's just call it c. It's like the Pythagorean Theorem. Okay, and then we also can say that tangent of the angle is y over x, thereby saying that the angle can be found by applying inverse tangent. So inverse tangent of y over x is going to give us our angle. Well, how do we go the other direction? Well, what if we were just given that this was 13 units long and we knew the angle was some theta? How would we find the pieces? Well, think about that triangle again. This is some x and this is some y. If you just looked at the two basic trig functions, sine and cosine, if we just said cosine of theta would be the adjacent piece over the hypotenuse. And if we rearrange and solve for x, wouldn't we just say that x is just 13 cosine theta? And if we did the same thing for y, we could just say that sine theta equals y over 13. So then y equals 13 sine theta. And if you take a look at that, aren't we just saying that the horizontal component is just the magnitude times cosine theta? And doesn't multiplying by cosine theta just retrieve the horizontal piece of the vector? And hopefully we'll be safe with that. And the vertical piece is just 13 sine theta. Again, if this is 13, if you multiply by sine theta, you get the vertical piece in return. So if you are given a vector and you want to break it down into its pieces, you just use cosines and sines. If you're given the pieces, well then you can just use the Pythagorean Theorem and inverse tangent to find the magnitude and direction. So we can easily go back and forth between these two things. Okay, so let's take an example. Let's look at vector p, and we'll use p because it's the vector of some plane. And let's say that's, again, we'll just stick with 5, 12. and then it's going to experience some wind, and let's say the wind is 3, -4. Okay, so let's get an idea of what's going on here. So our plane, these are our plane's velocity and the wind's velocity vectors. So this plane is flying, let's say, 5 meters per second east and 12 meters per second north. So it's dictated by that red. The wind is blowing east, but it's blowing south. And what we want to do is we want to find the resultant. Again, the resultant would be the addition of the two. So let's draw this. So there's the plane. And I'll try to draw this to scale. There's vector P. And we're going to add that to the wind. And the wind, is something like this. And so graphically, how do you add those together? Well, you add them tip to tail. And so we would just draw our plane and then add the wind. And then together, this blue line then is what they call the resultant. And really that's just the sum, the vector sum of the plane plus the wind. And it makes sense. Look at our resultant. It's longer to the right. Well, of course it is. The plane's going 5 and the wind's going to add 3 to it. So now we're 8 to the right. And then it's not as tall because the wind vertically is hurting the plane, right? See how vertically they're in the opposite direction? The plane's going north and the wind is blowing south. Now, if we actually just added those algebraically, if they're in component form, it's super easy. We would love if everything was in component form, because if we do P plus W, we just add the parts, and we get 5 plus 3 is 8, and 12 and 4, and 12 and -4 give us 8. And hopefully this looks something like 8 to the right and 8 up. That's what the addition of the plane plus the wind is. And so there are thousands of examples, whether it's adding velocities, adding forces, adding momentums together, where we're interested in adding or subtracting vectors. Graphically, you can see we add them tip to tail. Algebraically, we just add each corresponding piece. If this was in 3 dimensions, it'd be just the same. It'd be really hard to draw, but we would add the x's together, add the y's together, and add the z's together. We can even multiply by a scalar. We could say something like, well, what is 4p? Well, 4 would be a scalar, right? It's just a number. And we'd multiply it by p. Well, that's just 4 times 5, 12. Well, that's just 20, 48. And what we would notice is that this is just 4 copies of p. So on a graph, this would just be 1, 2, 3, 4. Hopefully you can see that this ratio, 12 to 5, is the exact same ratio as 48 to 20. 4p and p have the exact same angle. 4p is just 4 times longer. Each piece is 4 times longer, which makes the vector 4 times longer. So it's really easy to multiply by a scalar. We could even do things like 4 vector p minus 3 w's. And again, we could multiply by 4 and 3, and then we could subtract. Okay, what is the hard part then? Well, the hard part comes in, and again, this part here, you can put a star next to it. This is by far the most popular thing you're going to do in AP Physics. AP Physics, we just don't do much. This is just too easy. And again, this is kind of basics, what you hopefully learned in geometry or like pre-calc, of breaking down what a vector is. What we do most of the time is we look at adding and subtracting multiple vectors when they're given in magnitude and direction. Okay, so I'm going to give you a story. Not a difficult story. There's some object here, and there are 3 separate ropes attached to it. We'll go with a rope here, and we'll say the force is 20 newtons, and we'll say this angle is 30 degrees. There's another rope that's pulling straight down, so a different person is pulling down, and straight down at, let's say 15 newtons. And there's another person pulling over here that, let's say, is pulling at 25 newtons at an angle of 50 degrees. And what we want to do is sum all 3 of those up. And what we have to do is break them down into the pieces. If they were already in their pieces, it'd be really easy. We would just add each piece. So what we need to do is we need to come over here and apply this knowledge. So let's look just in the horizontal direction. And again, I'm going to use this thing called x hat and y hat. Let's define what that is. X hat is just the unit vector, which is 1 unit long, which points straight to the right. It's basically just saying, hey, I'm horizontal, and the y unit vector is 0, 1. Again, they're unit vectors because they're 1 unit long, and they just give you a direction. Meaning if I gave you 4x hat, it would be pointing 4 straight that way. Okay, so what we want to do is we want to take the horizontal pieces. This guy is going to go to the right. Well, how much to the right? Well, think about it. If I want the horizontal component of something, I just take the magnitude times cosine theta. So let's find this one. So that's 20 cosine 30. That's this horizontal piece. And I add to this horizontal piece. But in this case, I'm going to subtract because this guy's left. 25 newtons at cosine of 50. This rope doesn't do anything to help it move to the right or hurt it in the right, so it's straight down, so it doesn't have a contribution. And in the y direction, this is 20 newtons sine of 30. This is positive, so plus 25 sine of 50 minus straight up 15, because it's down. Again, think about this. This is the right versus the left. That's this piece versus this piece. And that would give us some sum. Okay, you type it out and you get some number. This has a vertical piece and this has a vertical piece. Both of them are right here. And again, you have to really think about why multiplying by cosine and sine gives you the horizontal piece and the vertical piece. And again, it's just basic geometry and trig. And then 15, I just subtract 15 with no angle because 15 is straight down. And that's what we're doing. Okay, combine those three things and again, it'd give you a number. Okay, so that'd give you the total resultant horizontal and vertical. And then when you do with that, well, that's the easy part. Once you're done, then what you have here is you have a horizontal component and a vertical component, and all of a sudden, so this is some total x and total y, and then you'd use the Pythagorean Theorem to find the magnitude and the angle to find that. Okay, so this is the key problem. You need to take whether these are momentums, whether this is velocities, whether these are three forces. In this case, I just happen to use force. A force and an angle, a force and an angle, and a force. Break them down, combine them, and then once you're done combining them, you basically have this. You have an x and a y, and then you put them together using the Pythagorean Theorem and inverse tangent to find then the total resultant magnitude and direction. And I'll leave that to you to kind of take a look at. Okay, again, this problem is something that we'll do the entire year. These are just kind of the basics, but this is the problem you really want to concentrate on. Okay, two more really small things, and then I'll let you go. In the textbook, you're going to see x hat, y hat, and occasionally we'll do 3 dimensions in z hat. Again, those are just directions, they're unit vectors. But you also might see I, j, and k. And I don't want you to flip out or anything. It's the exact same thing. I, j, k, x, y, z, same. Horizontal, vertical, and then depth. Right, so I is this way, j is this way, and then k and z would be pointing like out of the page. Okay, so we can do 3 dimensions. We can do all of this in 3 dimensions, adding and subtracting. Let's think about the magnitude in 3D. That's one of the things that will show up in the bookwork. And I'm going to draw you a picture here. How do you find the magnitude of 3D? So we're going to go right, up, and then out of the page. And I'm going to draw, and my drawing is never very good, but let's give this a whirl. So here's this box, okay? And I'm going to call this the bottom front left. And again, if you can visualize the box like I can, this is kind of the top of the box. Okay, and this right here is kind of the side of the box. Okay, so I want to go from here to here. So I need to go over, over, and up. So in 3 dimensions. Let's just pick some things that work out really nice. Let's say this is 3, 4 over, and then I have to go up 12. So this distance right here up is 12. And so my question is, how long is the string going to take from here to here? So let's think about this. First, let's look at just the bottom of my box. The bottom of my box is 3, 4. So how long would a string have to be if I just went straight across the bottom? Well, that's a 3, 4, 5. So that distance is 5. But now, this bottom, and then the vertical 12 goes up. And then this is the string. This string goes from this point to this point. But this is 5, and this is 12, and you have to convince yourself that that is indeed a right angle. Remember, this 5 is going straight across the bottom of the box, diagonally, and then the 12 goes straight up from there to the top of the box. Well, this forms a right angle. And so this is another 5, 12, and 5 squared plus 12 squared is 13 squared. And so how did we get 13 squared? Well, what's the 5? The 5 is a 3 and a 4. So I'll break this down. The end goal was 5 squared plus 12 squared was equal to 13 squared. But where did the 5 squared come from? So if we replace the 5 squared, it came from the fact that we had 3 squared plus 4 squared, and then the 12 squared is right there, and then lo and behold, you'll see that the three-dimensional Pythagorean theorem is just like the 2D one. This was just the x part squared plus the y part squared plus the z part squared equals the total distance squared, and we've derived the three-dimensional Pythagorean theorem. Okay, and again, we don't use this much. It doesn't show up on the AP, but it's in a couple questions. One of the questions is, I think you're flying a helicopter and you are so far east, north, and then you're above the water. So you're in 3 dimensions different than someone you're trying to save over here, and you want to know that distance, where you're going to have to do some stuff like this. Vector notation has this little arrow on top. Every now and then they bold it. But if they give you this is just giving it to you in component form, which you can use trig in the Pythagorean theorem to find the magnitude, which is the length of the vector, and then the direction. You can use cosines and sines to break down a vector into its pieces. You add and subtract vectors graphically by tip to tail. Algebraically, you just add their pieces and combine. You can multiply by a scalar, which just makes that same vector 4 units longer. It still maintains the same direction. Most of the time, our problems are like this, where you're given 3 vectors, not in component form, they're in this form. And the first thing you have to do to combine them is break them down into their pieces, and then recombine them at the end. I, J, K, X, Y, Z, all the same thing. And then at the very end, I threw in a little 3-dimensional Pythagorean theorem. You can even use graphical to add those 3 together. It doesn't even matter what order. You can start with any of those you want. If I took the 20 Newton one, and then I added the 25 Newton one, and then I did the 15 Newton one. Okay, my picture, and again, this is a really raw picture. I'm predicting then that your answer over here should have a negative x value and a positive y value. And I'm not sure that's going to be true. I'd have to really look at those numbers. I just hand drew this, this, and this in their angles. But a picture, if it was conclusive, would give you a real good idea. Like this picture over here, we clearly knew that the resultant had to then have a positive x and a positive y, which it did, 8, 8. I hope this helps get you started on vectors. Again, it's not everything, but it's at least a good start.